In Lab 1, I will be presenting my findings on the motion of an object as it travels at a constant velocity. The purpose of this lab was to analyze an object's motion traveling at a constant velocity, which is the same speed without a change in direction, through analyzing a video of the motion using Tracker, as well as developing a computational model to describe this motion using GlowScript. I will be analyzing the motion of a can rolling across a table. In the Tracker video that will be shown shortly, the orientation is rotated so that the can looks to be rolling in the negative y direction. Overall, the model is very consistent with Tracker's observed results, differing by only about 0.4% of the final position. From the video in Tracker, it is observed that the ball slows down very slightly just as it reaches the end of the video. Other than this time frame, motion of the can seems to be relatively consistent. This is also seen in the graph to the right that shows a linear plot. For the GlowScript code model, I made adjustments to the starter code by using Newton's second law to determine how the velocity and position would change based on the problem statement. From Newton's second law, I rewrote the equation to allow for velocity to be present in the equation. Because the problem statement assumes that there are no net forces acting on the can, the change in velocity must be zero. This is true whether there is a force acting on the can or not. If there are no forces to stop the motion, then the can will stay in motion. And even if forces are present, the velocity can remain unchanged if the forces acting on the can cancel one another out. From here, I was able to deduce that the average velocity would be the change in the final and initial positions divided by the corresponding change in time. Because the problem's assumptions allow for no change in velocity, the initial and final velocity would be equivalent. In order to make the GlowScript model as mathematically accurate to the Tracker results as possible, I set the time step equal to 0.042 after changing my recording rate, which was 24 frames per second, and set the overall time interval to 0.985 seconds, which was the length of my video. From there, I calculated the average velocity that would be used in the model in two different ways. First, I found the average velocity between the first two time frame points observed in Tracker, and used this value, which was negative 0.357 meters per second, in the computer model. Then I found the average velocity using the initial position at time 0 seconds and the final position at 0.985 seconds. This average velocity was much lower at negative 0.146 meters per second. From there, I organized the data at each time step into a table to be shown graphically for comparison. You can see between these two numbers that the final positions are drastically different between the two average velocity calculations, where the one with using the initial positions was much closer to that of the Tracker results. From there, I was able to use this table to make a graphical representation of my results. The Tracker results are represented by the blue line. The model using the initial velocity as the average velocity is in orange, and the gray line is the motion with the average velocity calculated from the starting and end positions found in Tracker. It is clear that the initial velocity estimate was much more accurate description of the motion observed in Tracker than the motion given by the model that uses the ending position in the calculation. Some important concepts to consider when analyzing these results are how axis orientation affects the results and why exactly the net force is used in motion calculations. For axis orientation, the can's motion could have been oriented to show movement in the positive x or negative x direction if I were to rotate my video. Regardless, the magnitude would be the same, but the direction of the motion would be different. This would be the case if my axis were to be rotated in the positive y direction as well. The only difference would be that the motion would be represented with a positive slope instead of a negative slope. The magnitudes would still be the same. In regards to the net force can be calculated based on how the object's motion changes or does not change. This is determined from a change in velocity over time, which can be determined from changing position over time, which can easily be measured. However, it is very difficult to know for sure how many forces are acting on an object to make a particular motion possible. For example, the can knowingly has forces like gravity, normal force, and friction that affect its motion. But there may be many more small and/or unknown forces at work on the object that could change the expected results. In this lab, The variation between the tracker results and the glow script model are due to the fact that there are these forces at play on the object, even though they may seem relatively small and insignificant.